Welcome back, viewers, to my physics channel. This is Dr. DORCAS NGIGI. We are moving on with our topic of thin lenses. Okay. Now, the last two topics we've been together. The last lesson we looked at the ray diagrams, and we looked at three different rays. Okay. We looked at one, the array that is that hits the lens passing through the optical center. And we said that ray passes undeviated. The other ray we looked at is a ray that hits the lens parallel to the principal axis. And we said that ray, by a convex mirrors, it will be refracted through the principal focus. By a diverging lens, that is a biconcave, it will be refracted such that it will appear like it was coming from the principal focus. The third ray diagram that we looked at was for a ray that strikes the lens passing through the principal focus. And we said that ray will be refracted parallel to the principal axis. And for a diverging lens, it hits the lens as if it wants to go through the principal focus. And when it hits the lens as if it wants to go through the principal focus, of course it will not go through the principal focus, but it will look like it wants to go through the principal focus, and it will also be refracted parallel to the principal axis. Those are the three rays that we looked at. We looked at their ray diagrams. And we said those ray diagrams are very important because they are the ones we are going to use to be able to get images by these lenses. Okay? So today we are going to look at image formation by converging lenses. Now remember, we said converging lenses are by convex or just convex lenses. So we're going to look at image formation by convex lenses. So welcome, let's get started. Okay. So image formation by convex lenses. Okay. So we said when we are drawing a lens, we don't draw the whole of it, we just draw a vertical line. Then on top there and below there, we indicate the kind of lens that we'll be using. The other thing we drew was the principal axis, which we say is a horizontal line parallel to the principal, perpendicular to the lens, and passing through the optical center, passing through F, and passing through the center of curvature. We also say that this, because it's a biconvex, then it has two centers of curvature and two focuses. Okay, that's very important. Now the other thing we said is this: from the center, from the optical center to the center of curvature, we call that distance the radius of curvature, and we said it is twice the distance from the optical center to the principal focus, the distance we called the focal length. So meaning the center of curvature is twice the focal length. So instead of writing now C, I can write it as 2F. I can write it as 2F. That way, you'll be able to understand better. So the center of curvature is what we have indicated as 2F. Why? Because the distance from the optical center to the center of curvature is twice the distance from the optical center to the principal focus. So this distance here is twice this distance here. So instead of saying center of curvature C, I can as well say 2F on both sides. So that, I hope you don't get confused when I put 2F instead of C. It is still the center of curvature. Okay, so today we are going to start with an object at infinity. So what is an object at infinity? When you talk about infinity, we are talking about an object that is very far, that is with respect to the lens. It may not be very far to our eyes, but with respect to the lens that we are using, that object is very far. For example, if we want to observe the clouds or some sky or some trees that are very far, to our lens, that is an object at infinity. Now, when an object is at infinity, the rays come to the lens parallel to each other. That's number one. They come to the lens parallel to each other. Now, we can draw two rays that are parallel to each other. Like that, okay? So these rays are parallel to each other. Remember, they are not parallel to the principal axis, but they are parallel to each other. They're making an angle. As you can see, this one is making an angle with the principal axis. Now, these rays are coming from infinity. So it's a place we cannot exactly say where it is because it's very far. Now, when those rays come like that, then how are they going to be refracted? Now, number one, we said a ray that comes and strikes the lens, passing through the optical center, we said that ray passes undeviated. So that is going to continue straight. I hope my line is looking straight. So something coming, that's much better. Now that ray passes undeviated. Okay. Now the other thing is the other ray that is parallel to it. Now that one is not passing through the optical center, and therefore we expect that ray will be refracted. But the question is, how will it be refracted? Now there's a line we called the focal plane. There's a line we called the focal plane, and we said is a vertical line that is perpendicular to the principal axis and passing through the principal focus. We said there's a line we call the focal plane, which we defined as the line that is perpendicular to the principal axis, so it's making an angle of 90 degrees to the principal axis, and it is passing through the principal focus. Now, these rays that are coming from infinity, they are coming parallel to each other, and they intersect after refraction somewhere at the focal plane. They intersect somewhere at the focal plane, something like that. So this ray should continue like that after refraction. Okay, so the first one passes undeviated, because we said any ray that passes through optical center, or that one passes undeviated. The other ray is parallel to it, and so that one will not go undeviated. It will be refracted. But after being refracted, then it will be refracted in such a way that it meets the other ray at the focal plane. So the focal plane is that vertical line. And therefore, where they meet, that is where we form our image. So what do? We draw an arrow head, and then we raise that line to meet the principal axis. Okay, something like that. So these are just the first ray passes undeviated. The second ray changes route after refraction by the lens to pass there. Now where they intersect, that's where we form the image. Now if we look at that image, what can we see? Now you can see that that image of ours is formed at the principal focus. That image of ours is formed at the principal focus. Okay, like that. So what can we say about the image formed by the lens for an object that is at infinity? One, that image is formed at the principal focus. So let's write the image characteristics. So number one, image forms at F. F is the principal focus. So image forms at F. Number two, as you can see, it is inverted. It's upside down. So it is inverted. Number three, it is a true image. Now we're going to understand the difference between a true image and a virtual image as we continue. So a true image is the one that is able to form on a screen. A true image is an image that is able to form on a screen. That's a true image. And it is always upside down. If the object is upright, that image will be, is standing, the image will be looking upside down. If the object is upside down, then the image will be upright. Okay, and number four, this image is smaller than the object. So it is diminished. It is diminished or smaller than the object. Okay, so we have formed our first image, and we have formed an image of an object that is at infinity, an object that is very, very far. And we are able to form that image because we say the rays come parallel to each other. So the one going through the optical center passes and deviated. The other one will be refracted, and after refraction, the two refracted rays meet somewhere on the focal plane. A focal plane is that vertical line passing through the principal focus and perpendicular to the principal axis. So simply, the image is formed at the principal focus. What are the characteristics of the image? It forms at the principal focus. It is inverted, upside down. It is a true image, meaning it can form on a screen. And it is diminished, meaning it is smaller than the object. Okay? Now, the other thing we're going to do, we are going to bring our object a bit closer. So we move it from infinity and we bring it behind the center of curvature. We move it from infinity and we bring it behind the center of curvature. So I don't know whether this space is too small. I'll try to use it. Let's say F is there, and there's 2F, and we have F, and we have 2F. This is our optical center. So let's place our object somewhere behind 2F. Let me place it there. Okay. So the object is behind 2F. So object behind 2F. Remember, 2F is our center of curvature. So if I press that object behind 2F, then what would be the characteristics of my image? Okay. So we're going to follow the rules that we already know. So rule number one, a ray that is coming from the tip of the object parallel to the principal axis, like that. Now that ray is going to be refracted through the principal focus. Like that. Okay? Hope you remember that rule. The other rule is any ray that is coming from the tip of the object to pass through the optical center should pass undeviated. So this ray should come from here. The line looks so curved. Trying to draw a straight line, but not very easy. Hope that is a bit straight. curvature. Now, the ray that's coming from the object to pass through the optical center, that ray passes undiluted. Remember that ray diagram? The other ray is a ray that is parallel to the principal axis and close to the principal axis. That ray, after refraction, should pass through the principal focus. Now, where the two rays meet, that is where we have our image. That is where we have our image. So what we do, at that point, we draw an arrowhead like we did in the first case. And then we are going to draw a straight line to intersect, to touch the principal axis, like that. So that is our image. Okay. Now when we look at the image, I can remove these lines. Now when you look at that image, so that's our object, and that's our image. What would we say are the characteristics of that image? So let's look at characteristics. So, 1, it is inverted. As you can see, our object is upright, but the image is inverted. Okay. 2, it is true. One way to check whether it is true, if the object is upright and the image is inverted, then that image is a true image. So it is true, and true, like I said before, it means that image is an image that can form on a screen. Number 3, that image in terms of size, if you look at the size of my object and the size of my image, then you can see the image is smaller than the object, so it is diminished. And number 4, let's talk about where the image has formed. Okay, when the object was at infinity, the image formed at the principal focus. When we move the object closer from infinity to somewhere behind the center of curvature to F, then now the image moves further, and so the object moves closer to the lens as the image moves further away from the lens. So the image now has moved from F to somewhere between F and 2F. So image formed between F and 2F. Okay. So we have formed two images already, of an object at infinity and of an object that is behind the center of curvature. In both cases, our images are inverted. They are true. They are diminished. But the one at infinity is forming at F, while the one that is behind the center of curvature is forming between the principal focus and our center of curvature. Now I want us to move the object closer now. We have moved from infinity. We are behind behind C, that is 2F. Now what about if I move now my object to 2F? Now let's see what happens when the object is between. No, I didn't have to wrap everything. I just redraw. Remember, when you're drawing, I don't have, not using a ruler, so I'm not drawing to scale. Make sure you are the distance between, from the optical center to F on this side is equal to the distance from the optical center to F on the other side. From the optical center to 2F must be equal from the distance from the optical center to 2F on the other side. Number 2, the distance from the optical center to 2F must be twice the distance from the optical center to F. You must draw that to scale so that you don't get wrong images and be falling in the wrong places. Now our object, now we have moved it to F. Okay, so image at 2F. So image now, the object is at 2F, meaning is at the center of curvature. So from infinity to behind the center of curvature to the center of curvature. Now very simple, we are going to repeat the same procedure where we have a ray that is coming parallel to the principal axis. That's the first ray diagram. And the ray that is parallel and close to the principal axis, that ray must be refracted through the principal focus. Okay. The other ray is a ray that comes from the tip of the object to pass through the optical center, and that ray should pass undeviated. Okay, it's not very straight, a bit of a hard time there. A bit better. Now that ray intersects where the two rays intersect. Now that point is where we have the image. Now I also draw a vertical line to somewhere there. Now if you draw properly, then you would find that the point where the ray hits the image touches the principal axis, that point should be our 2F. That is, if you draw properly to scale. So if you look at that, it's not very straight. So I'm not able to draw very well to scale. I don't have a ruler, I don't have not measured. So that point there should be at least our 2F. Okay. Now characteristics. So image characteristics. So one, which is very obvious, it is inverted. And if it is inverted, it means it is true. Can form on a screen. Number 3, let's look at the position. So formed at 2F, which is our C, center of curvature. And number 4, if you draw to scale, then you will see that your image and your object are of the same size. So we'll say same size as the object. Okay, so if you want an image that is the same size as the object, then for a converging lens, then you put the object at the center of curvature. So when the object is at 2F, then the image will also form at 2F. What else? The image will be true, and so it will be inverted, and it will be the same size as the object. Okay, now let's look at the other one. Now let's move our object much closer to, let's move our object closer. What would happen now if we move the object now from 2F closer to, remember we are moving towards the lens from infinity to behind 2F to where 2F is. Now we are moving much closer to the lens. Let's put our object between 2F and F. Okay? Between C and F. Now what would be where would the image form? And what would be the image characteristics? Now by now you are getting the pattern. We are using only two ray diagrams. One which is parallel to the principal axis, which is refracted through the principal focus, and the other one that is passing through the optical center, which passes undeviated. Okay? Okay, so with that, let's show the other one. So this was object at 2C. Was object at 2F, object at C, or object at 2F, and these are the characteristics. Now I'm going to delete these ones so that I get space to draw the other image. So object between 2F and F. Object between 2F and F. Okay. This F. That's 2F. That's F. That's 2F. Okay. You know whether space will be enough. It may not put a very big object. That's our object. So let's follow the rules. The ray that is parallel to the principal axis from the tip of the object, that ray will be refracted through the principal focus. Okay, so it's moving far away from the lens, passing through the principal focus after refraction. So the other ray is the ray that is going to hit the lens, passing through the optical center, and that one is to pass undeviated. Something like that. Okay, so where do they meet? They meet there. Where they meet, you draw an arrowhead, of course, facing down because they face on the lower side of the principal axis, and you draw a straight line to intersect the principal axis. Something like that. Now, if you draw to scale, then yours will be much better. So what can you say about that image? So image characteristic. One, that is very obvious, is that it is inverted. Two, it is true. The fact that the object is upright and the image is inverted means the image is a true image. So meaning it can form on a screen. Number three, what can we say about the point where it forms? It forms behind the center of curvature. So forms behind 2F. And lastly, the size of the image compared to the size of the object. Now if you take a good look, you can see the image is bigger than the object. So it's magnified. Okay, or simply is bigger than the object. Okay, so we are almost there. So we started with an object at infinity. So behind 2F, at 2F, now between 2F and F. And we are seeing when the object is between 2F and F, then our image is forming behind 2F. So what pattern are we seeing here? As we bring the object closer to the lens, the image moves far away from the lens. As the object moves from infinity, coming closer towards the lens, the image moves from F, the closest to the lens, and moves away from the lens, further away from the lens. Okay, so that is very important. We need to check that. We're going to use that much later. Okay, now where do we take the object now? The next point we can put the object is at F. Okay, so what if I move the object from between 2F and F, and put it at F, at the principal focus? So object at F. Okay, so now instead of 2F, I have object at F. Object at F, so it's there. So we follow the same rules. A ray that is parallel to the principal axis should be refracted through the principal focus. So after refraction by the lens, that ray should pass through the principal focus, like that. Okay. Now the other ray should pass through the optical center, and that ray should pass undeviated. Those are the two rays. Okay. Now if you take a good look at the two rays, for an object that is at F, this is our object. Now you can see that the rays come out parallel to each other after refraction. The rays come out parallel to each other after refraction, so that even if I produce the two lines backwards, they will also go backwards as parallel lines. Okay? So, where are these lines going? Where do we form the image then? Now we know that parallel lines, we say they do not meet. And let's assume they meet. Where will they meet? They will meet very far, somewhere at infinity. Okay? So whatever image we are going to form, that image will be formed at infinity. Remember, anytime we move closer to the lens, the image moves further away from the lens, such that by the time we reach F, the object is at F, then the image is forming very far from our lens, somewhere at infinity. Remember the law of reversibility of light? We talked about that in the last lesson, that light remembers its path. It retraces its own path. So if the object is at infinity, the ray will be coming from the object which is at infinity, will come parallel to each other, and the image will be formed at F. Now, the object is the one that is at F, and the rays remember their path. So after refraction, they are going to form the image at infinity. Please don't forget that. So this is object at F. So image at infinity. Now let's try to imagine the characteristics of that image. If you were to give the more characteristics of that image, what would you say? I would say it will be a true image. Okay? Because these lines are going to intersect. By the time we reach infinity, they will have intersected. So it will be a true image. It can form on a screen if we can be able to go to the infinity and put our screen there. So it will be inverted. It will be true. It will form at infinity, but it will be much, much bigger than our object. Remember, we said if the object is at infinity, the image will form at F, and it will be smaller than the object. Now that our object is at F, the image is at infinity. Remember, as we are going further away, as the image goes further away from the lens, it becomes bigger and bigger. You're seeing the case just before that. So this image that is forming at infinity is going to be even bigger than our object. It will be more magnified. Okay? So lastly, let's move our object in front of F. So put it between the principal focus and the optical center. Okay, so let's move the object. Okay. So let's put the object between this optical center and this our F. So what if I put the object between my F and my optical center? Let's make it a bit smaller. That's our object. So object between F and O. Okay. So follow the same rules. The first rule, the ray is parallel to the principal axis, coming from the tip of the object, and that ray should be refracted through the principal focus. Something like that. Okay. The second ray should come from the tip, passing through the optical center, and that ray should pass undeviated. So this ray is moving through F, and the other one is passing through the optical center, and it is passing undeviated. Okay, now if you compare these rays and those rays, then you see there's a difference. These are parallel rays, but these are diverging rays. Okay, they are diverging rays, may not appear very well, but they are diverging rays. They are moving further and further away from each other. So they are true rays. Remember, they are true rays. The ray has come from the tip of the object, has passed through the optical center, and has passed through undeviated. The other ray is a true ray, hits the lens. Then after refraction, it is passing through the principal focus, which is a true focus, remember, and it is going its separate way. Now those are true rays. But your eye, if your eye is here, where will these rays look like they are coming from? If you press your eye there, these rays look like they are coming from somewhere, because remember they are diverging rays, and diverging rays come from a certain point. Okay, so if you produce these diverging rays backwards on a straight line, okay, try to make the line straight. Then those rays look like they are coming from somewhere, because they are diverging rays, so they came from somewhere. Now I put dotted lines because the truth is they are not coming from there. They are coming from the lens. They have been refracted. Anything that I draw beyond that point, that is imaginary. But the imaginary rays intersect somewhere. They intersect somewhere. So where they intersect, I draw an arrowhead. Then I'm going to produce the line downwards until where we meet the principal axis. Now why am I drawing the line dotted? Because we have formed that intersection by the intersection of two imaginary rays. This is not a true ray. neither is the other one a true ray. The true rays are the ones that are going away from our lens after refraction. So anything we are drawing backwards is just the eye which is seeing as if, remember, your eye can only see a straight line. So it is seeing as if this ray is coming from here and this ray is coming from there. But the reality is the rays are coming from the lens. So anything behind that point is imaginary. So when two imaginary rays intersect, then we form a virtue image. So this is our image. It is virtue. That's why you see it is upright, just like our object. So image characteristic. So the characteristics of that image, 1, it is upright. So that is the first upright image that we have formed using a convex lens. Okay, the others were true, so they were inverted. So 2, it is virtue. It is virtue, it is not true. If it were true, then it would have formed on a screen, and it would have formed by intersection of true refracted rays. Now it is forming from intersection of 2 virtue or imaginary rays. So it's a virtue image. Number 3, if we talk about the size, it is bigger than the object, so it is magnified. So bigger than the object. And lastly, number 4, where does it form? It forms same side as the object. So the image and the object have formed on the same side. So that is the last image we have drawn of a concave mirror. So we have seen there are 2 magnified images. One is when the object is between F and the optical center. The image is magnified but virtue. The other magnified image that we saw was when the object was between the center of curvature and the principal focus, where the image formed behind the center of curvature, but it was true but magnified. So that the true magnified images that we form. Of course, when the object is at F, there will be a very big image at infinity, only that now that one we cannot be able to draw it. Now that brings us to the end of this, but before I close, we say this, why are we talking about rays coming from a point? Any object that you have is a source of light. I want you to see an object as a potential source of light. So there are so many rays that are coming from a single point. Okay, so if you talk about one point on an object, there are so many rays that are coming from there as long as light falls on that object. So out of these many rays, there is the one that will be parallel to the principal axis, so it will be refracted through the principal focus. There is another that will be passing through the optical center, so that one passes undeviated. So after refraction, when they meet, then we form the image. You can also have another one that is passing, for example, through F, that is for object that behind F. The one that passes through F should be refracted parallel to the principal axis, and the result will just be the same. So that brings us to the end of our lesson. Don't forget to like and subscribe. And also, I hope to see you in my next video, where I'll be talking about characteristics of images formed by concave lens. So for now, goodbye.